What if I told you that the entire universe has been quietly telling us its oldest story for billions of years? A story written in light so ancient it predates the very first star. This isn't science fiction. It's real, and it's happening right above us every moment of every day. There's a faint, nearly invisible glow that fills every corner of the cosmos, an echo from a time when the universe was nothing more than a hot, dense sea of particles and energy. This is the cosmic microwave background radiation, the oldest light in existence. It's the afterglow of the Big Bang itself, a snapshot of the infant universe, captured forever in the cold, dark expanse of space. Think of it as the universe's first photograph taken when everything was just 380,000 years old. At that moment, the cosmos cooled just enough for light to break free and begin its journey across space and time. That light is still traveling, still reaching us, carrying with it secrets about how everything began. Hidden within its subtle patterns are the answers to our biggest questions. What is the universe made of? How did galaxies form? What is dark matter? And why is the expansion of the universe speeding up? These aren't just abstract ideas. They're clues embedded in this cosmic fossil record, waiting for us to decode them. In this video, we're going to unravel that story together. We'll explore how scientists first stumbled upon this whisper from the past, how satellites have mapped its delicate imperfections, and what these discoveries tell us about the nature of reality itself. You'll come away seeing the night sky differently, not just as a beautiful scattering of stars, but as a living historical document, a cosmic diary written in the language of light. So let's begin this journey back in time to the very dawn of everything. Picture the universe in its earliest moments not as a vast, star-filled expanse, but as an unimaginably hot, dense fog of energy and particles. For the first several 100,000 years, it was so intensely hot that atoms couldn't even form. Electrons and protons moved in a swirling, opaque plasma, constantly scattering light, trapping it like headlights in a thick fog. Then, around 380,000 years after the Big Bang, something extraordinary happened. The universe had expanded and cooled just enough, down to about 3,000 degrees Celsius, for electrons and protons to finally combine and form neutral hydrogen atoms. This pivotal moment is called recombination. Think of it like a cosmic clearing of the fog. Suddenly, light that had been bouncing around, trapped in that hot plasma, could travel freely across space. That first burst of light has been journeying across the cosmos ever since, stretched and cooled by the expansion of the universe over billions of years. Today, we detect it as a faint, cold signal coming from every direction in the sky, the cosmic microwave background. It's the oldest light we can observe, a direct messenger from the universe's infancy. But this ancient light is far more than just a uniform glow. When scientists finally mapped it with incredible precision, they discovered it wasn't perfectly smooth. There are tiny variations, minute differences in temperature, on the order of 1 part in 100,000. To put that into perspective, if the cosmic microwave background were represented by a perfectly smooth ocean, these fluctuations would be ripples no taller than a few centimeters. Yet these tiny imperfections are the most important part of the story. They are the seeds of all structure in the universe. Those slightly denser regions, revealed by marginally warmer spots in the background radiation, had just a little more gravitational pull. Over eons, they attracted more and more matter, eventually collapsing under their own gravity to form the first galaxies, stars, and everything we see today. Without these initial density variations gifted to us by quantum fluctuations in the universe's first moments, the cosmos would be a vast, empty, and dark void. We owe our very existence to these faint fingerprints. This is why Nobel laureate George Smoot so poetically referred to mapping these fluctuations as seeing the face of God. It's a snapshot of the universe at its most fundamental level, showing us the initial conditions from which everything emerged. By meticulously studying the patterns and statistics of these temperature variations, cosmologists can test our most profound theories about the birth of the cosmos, including the period of hyper-expansion known as inflation, which is believed to have magnified those quantum seeds into cosmic proportions. These faint whispers from the dawn of time might even hold clues to physics we have yet to discover, realms beyond our current standard model. Sometimes the greatest discoveries in science don't come from a grand, targeted search, but from the simple act of paying attention to something everyone else might have ignored. That's precisely what happened in the early 1960s at Bell Labs in Homedale, New Jersey. Two young radio astronomers, Penzias and Wilson, were using a massive, state-of-the-art horn antenna. This unique instrument, originally built for pioneering work in satellite communication, looked less like a traditional telescope and more like a giant metallic ear, pointed toward the sky to listen to the faint radio whispers of the cosmos. Their initial goal was to study emissions from the Milky Way, but they were immediately plagued by a persistent, maddening problem. A constant, low-level hiss of microwave static that came from every direction, day and night, and simply would not go away. Convinced it was some form of terrestrial interference or an equipment flaw, they embarked on a meticulous process of elimination. They checked every electrical connection, measured the noise from the receiver itself, and even pointed the antenna toward New York City, suspecting some form of urban radio pollution. The signal remained stubbornly uniform. Their most famous and somewhat comical effort involved a pair of pigeons that had taken up residence inside the large horn of the antenna. Believing the birds and their, droppings might be causing the interference, they carefully evicted the pigeons and cleaned out the mess, what Penzias later referred to as a white dielectric material. Yet, even after this thorough cleaning, the mysterious hum persisted. It was a noise that had no obvious source, a signal with no apparent message. They were, quite literally, hearing the faint but steady hiss of the universe itself. Unbeknownst to them, a team of physicists at Princeton University, led by Robert Dicke, was actively building a radiometer to go looking for this very signal. They were working on a theory that if the universe had begun in a hot, dense state, a Big Bang, it should have left behind a cool, remnant glow of radiation that would now be detectable as microwaves. Meanwhile, Penzias and Wilson, frustrated but brilliant in their persistence, finally realized the signal they were trying to eliminate was not a flaw at all. It was isotropic, meaning it was perfectly uniform no matter where in the sky they pointed their antenna. After calculating its intensity, they found it corresponded to a temperature of approximately 2.7 degrees above absolute zero. It was the predicted afterglow. A fortuitous phone call connected them to the Princeton group, and the pieces fell into place. Penzias and Wilson had accidentally stumbled upon the strongest evidence yet for the Big Bang theory, the cosmic microwave background. Their careful, painstaking work to eliminate all possible errors is what gave the discovery its incredible weight. They could say with absolute confidence that this signal was real, and it was cosmic. In 1978, this monumental, accidental discovery earned them the Nobel Prize in Physics. It was a triumph of serendipity meeting rigorous scientific method. Their work transformed cosmology from a field of elegant mathematical speculation into a hard, observational science, proving the universe did indeed have a beginning. That humble horn antenna, once troubled by pigeons, became a monument to one of the greatest detective stories in scientific history, proving that sometimes you have to listen carefully to the background noise to hear the echo of creation. But confirming the existence of the background radiation was only the beginning. To truly understand the story it was telling, scientists needed to see it in incredible detail. They needed a map. That map arrived thanks to a satellite called the Cosmic Background Explorer, or COBE, pronounced COBE. Launched by NASA in 1989, COBE was designed with one extraordinary purpose: to look back in time and take the first ever detailed baby picture of our universe. For years, the signal discovered by Penzias and Wilson had been observed, but only as a uniform, featureless glow. The prevailing Big Bang theory, however, predicted it shouldn't be perfectly smooth. The seeds of all future galaxies had to be there, imprinted as infinitesimally small temperature differences, what scientists call anisotropies. Finding these wrinkles was the holy grail. It took COBE exquisitely sensitive instruments 2 years of scanning the entire sky to finally see them. When the team, led by astronomers John Mather and George Smoot, unveiled their results in 1992, the scientific world gasped. There it was. The universe's first light was not a bland, even canvas. It was mottled with a pattern of incredibly faint hot and cold spots, variations of just 1 part in 100,000. To put that into perspective, that's like looking at a perfectly smooth sheet of glass and finding hills and valleys no taller than a single sheet of paper. George Smoot, presenting the findings, made the famous and poetic declaration that it was like looking at the face of God. It wasn't just a beautiful metaphor, it was a profound scientific truth. Those tiny fluctuations were the cosmic fossils everyone had been searching for. They were the imprints of the primordial density variations, the slightly denser patches of universe that, over billions of years, would collapse under their own gravity to form everything we see: galaxies, stars, planets, and us. COBE had provided the first direct visual evidence for the origin of cosmic structure. It was a resounding, spectacular confirmation of the Big Bang model. But COBE revelations didn't stop there. Its other critical mission was to measure the precise spectrum of this ancient light. According to theory, the radiation from a hot, dense early universe should have a very specific signature known as a blackbody spectrum. The data COBE sent back was nothing short of perfect. Its curve matched the theoretical prediction with astonishing precision, a flawless fit that left no room for doubt. This was the final, definitive piece of evidence. The universe absolutely began in a hot, dense state. Furthermore, by analyzing the size and distribution of those tiny temperature fluctuations, COBE told us something fundamental about the shape of the cosmos itself. The data strongly indicated that on the largest scales, the universe is flat. In cosmological terms, a flat universe means that the geometry of spacetime is such that parallel lines will never meet or diverge. This finding was a critical piece of the puzzle, placing powerful constraints on the total amount of matter and energy in the cosmos, and setting the stage for the even more shocking discovery of dark energy that would soon follow. COBE didn't just take a picture, it gave us the universe's birth certificate and its basic architectural blueprint, all from listening to the faint whisper of microwaves from the edge of time. COBE gave us that first, breathtaking baby picture of the universe, but it was a bit like looking at an impressionist painting from a distance. You could see the beautiful patterns, but the finest details were still a blur. To truly understand the cosmos, we needed a sharper image. That's where 2 incredible missions came in, acting as the universe's most powerful prescription glasses. First was the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. Its design was a masterstroke of engineering, positioned not around Earth, but at a special gravitational balancing point a million miles away, known as Lagrange Point 2. This distant, stable perch gave it an incredibly clear and quiet view of the sky, free from the interference of our planet's heat and radio noise. For 9 years, WMAP meticulously scanned the cosmos, and the data it sent back was nothing short of revolutionary. It took the fuzzy, pixelated map from COBE and transformed it into a high-definition portrait of the infant universe. With this newfound clarity, scientists could measure the cosmic parameters with stunning precision. WMAP pinned down the age of the universe to an astonishingly accurate 13.77 billion years. It provided the strongest evidence yet for the theory of cosmic inflation, that moment of unimaginably rapid expansion in the first fraction of a second after the Big Bang. The mission also gave us a much clearer picture of the universe's geometry, confirming with even greater certainty that we live in a flat cosmos. But perhaps most importantly, WMAP didn't just look at the temperature variations. It began the crucial work of studying the polarization of this ancient light, the subtle direction in which those light waves are vibrating. This polarization is a fingerprint left behind by the very last interactions of light and matter, and it holds clues to what happened in those first frantic moments. Then, in 2009, the European Space Agency launched an even more advanced observer, the Planck satellite. If WMAP gave us high definition, Planck gave us ultra-high definition. Its instruments were so sensitive they could detect temperature variations of a few millionths of a degree. To achieve this incredible sensitivity, Planck's detectors had to be cooled to just a tenth of a degree above absolute zero, making it one of the coldest objects in the universe. For over 4 years, Planck mapped the sky with a resolution so fine it could distinguish details smaller than the apparent size of the Moon. The results from Planck refined our cosmic recipe to an exquisite level of detail. We now know with remarkable certainty that the universe is made of about 5% ordinary matter, the atoms that make up stars, planets, and us. 27% is the mysterious, invisible substance known as dark matter, which provides the gravitational scaffolding for galaxies. And a dominant 68% is dark energy, the enigmatic force causing the expansion of the universe to accelerate. Planck's measurement of the Hubble constant, the rate of that expansion, became the new gold standard for cosmology. But its most tantalizing contribution was in its detailed maps of the CMB's polarization. Within that subtle twisting of light, scientists are searching for a specific curl-like pattern known as primordial B modes. This signature would be the smoking gun for gravitational waves generated during the inflationary epoch, literally allowing us to probe the universe when it was less than a trillionth of a second old. Together, WMAP and Planck transformed cosmology from a field of broad-stroke theories into a precise science. They provided a foundational data set that every new cosmological theory must now answer to, constraining our models of the universe's origin and evolution with an ironclad grip. They didn't just give us a better picture, they gave us a precise and detailed blueprint for the cosmos, drawn from the faintest whisper of light that has traveled across nearly 14 billion years to tell its story. So, we have this incredibly detailed map of the ancient universe, but what are we actually seeing in those subtle temperature variations? It turns out the pattern is far from random noise. It's a precise, frozen record of sound waves rippling through the primordial plasma. To understand this, let's rewind the clock back to that moment just after recombination, when the universe first became transparent. At that point, the cosmos was filled with a hot, mostly uniform soup of photons, dark matter, and ordinary matter protons and electrons now bound together as neutral atoms. But it wasn't perfectly smooth. Thanks to those tiny quantum fluctuations from the inflationary epoch, there were minute differences in density scattered throughout. Think of these denser regions as having slightly stronger gravity. They began to pull matter inward, but there was a counterforce, the intense pressure from the trapped radiation, the light that was still tightly coupled to the matter. This created a tug of war. Gravity pulled matter in while radiation pressure pushed it out. The result was a series of spherical sound waves, or acoustic oscillations, pulsing through the hot plasma. These waves would compress the gas, heating it slightly, and then rarefy it, cooling it down, creating a predictable pattern of concentric rings of hotter and colder material. Then, at the moment of recombination, the music suddenly stopped. The photons decoupled and streamed away freely, and the sound waves were instantly frozen in place, imprinting their signature onto the cosmic microwave background as a series of hot and cold spots. When cosmologists analyze the CMB map, they don't just look at the spots themselves, they perform a sophisticated mathematical breakdown called a power spectrum. This chart plots the angular size of all the temperature fluctuations against their relative strength, and it's in this spectrum that the story becomes incredibly clear. The most prominent feature is a series of distinct peaks. The first and largest peak tells us about the geometry of the universe. It corresponds to the size of the largest sound waves that had just enough time to complete one full compression before the music stopped. Measuring the angular size of these waves on the sky acts as a standard ruler, because we know the actual physical size of these waves determined by the speed of sound in the early plasma and the age of the universe at recombination. We can use them to measure the curvature of the universe. The fact that this peak appears at a specific scale confirmed that we live in a flat universe, a finding of monumental importance. But the story doesn't end with the first peak. The secondary peaks are just as crucial. The second peak gives us a precise measurement of the density of ordinary matter, or baryons. This is because more baryonic matter means stronger gravity, which affects how far the sound waves could rebound after their first compression. The third peak and beyond are deeply tied to the amount of dark matter. Dark matter, which doesn't interact with light but does exert gravity, provided the underlying gravitational scaffolding. It helped pull everything together but didn't contribute to the radiation pressure that fought back. So, the relative heights of these peaks allow scientists to calculate the exact ratio of dark matter to ordinary matter. It's like listening to the harmonics of a musical instrument. The precise notes and their intensities tell you exactly what the instrument is made of and its physical properties. This entire acoustic fingerprint is a time capsule of astonishing precision. By reading these peaks, we can reconstruct the exact conditions of the universe at 380,000 years old with a level of detail that would have been unimaginable just decades ago. We know its composition, its geometry, and its initial density fluctuations. It's the single most important piece of evidence we have for our standard model of cosmology. Yet, this incredible picture is only half the story. The temperature variations tell us about the distribution of matter, but the ancient light holds another, even more subtle clue. Its polarization, the specific orientation of its light waves, which can reveal the very dynamics of how that light was set free. While the temperature map of the cosmic microwave background gives us a stunningly detailed picture of the infant universe's density, it's only half the story. The ancient light holds another, even more subtle, layer of information encoded in its polarization. To understand this, picture a calm pond. When you throw a stone into it, you create ripples that move outward. These are like the temperature anisotropies we've discussed, compressions and rarefactions in the primordial plasma. But if two sets of ripples cross each other, they can create a swirling, twisting pattern on the water's surface. In the language of light, this swirling pattern is what scientists call B-mode polarization. This specific curl-like distortion in the polarization of the CMB is the most sought-after signature in all of modern cosmology. The reason for the intense excitement is its proposed origin. It is thought to be a direct imprint of primordial gravitational waves. These aren't the waves from colliding black holes detected by LIGO, but something far more profound. Theory suggests that during the inflationary period, that split second of hyper-expansion, the fabric of spacetime itself was violently jostled by quantum fluctuations at an unimaginably small scale. Inflation would have then stretched these quantum tremors across the entire cosmos, magnifying them into literal ripples in the geometry of the universe. As these gravitational waves propagated through the primordial plasma, they would have gently tugged on the electrons, imparting a distinct, swirling pattern to the light that was scattering off them. That pattern, frozen in time, is the primordial B-mode signal. Finding this signal would be nothing short of revolutionary. It would provide the first direct, smoking gun evidence for the theory of cosmic inflation, confirming that such a monumental event actually occurred. But it would do far more than that. The strength of the B-mode signal is directly tied to the energy scale at which inflation happened. Detecting it would tell us precisely how powerful the inflationary field was, effectively allowing us to peer into physics at energy levels 1 trillion times higher than anything we can ever hope to achieve with particle colliders like the Large Hadron Collider. It would be a direct window into the grand unified theory scale, where the fundamental forces of nature are thought to merge into one. The hunt for these elusive B-modes has been one of the most dramatic and challenging endeavors in science. It's been led by ambitious ground-based experiments located at the Earth's most extreme and dry locations, like the South Pole, where the thin, arid atmosphere is ideal for observing these faint microwave signals. The most famous of these is the Bicep and Keck array series of telescopes. In 2014, the Bicep 2 team made global headlines with an announcement that sent shockwaves through the scientific community. They believed they had detected the telltale swirls of primordial B-modes. It was hailed as a monumental discovery. However, the elation was short-lived. Further analysis, crucially in collaboration with data from the Planck satellite, revealed that the signal they were seeing was almost entirely due to a much more mundane culprit: interstellar dust within our own Milky Way galaxy. This dust, when magnetically aligned, can emit polarized light that perfectly mimics the curl pattern scientists were desperately searching for. It was a sobering lesson in the immense challenges of modern cosmology, where the signal you're hunting is buried beneath layers of cosmic foreground noise. Yet the search is far from over. That initial disappointment only fueled more determined and sophisticated efforts. The lessons learned from the Bicep experience led to a new generation of experiments designed to observe the sky at multiple frequencies. This multi-frequency approach is key because the galactic dust signal behaves differently across various wavelengths than the pristine CMB signal. By comparing maps at different frequencies, scientists can meticulously subtract the dusty foreground, like carefully cleaning a dirty window to see the clear sky beyond. Next-generation projects like the Simons Observatory and the even more ambitious CMB S4 are now being built with thousands of ultra-sensitive detectors specifically designed to overcome this obstacle. They represent a colossal collaborative effort to finally capture this holy grail of cosmology, or to definitively rule it out if it remains forever elusive. This relentless pursuit exemplifies a profound truth about science. It is a self-correcting process, driven not just by the thrill of discovery, but by an unwavering commitment to the truth, no matter how challenging it is to find. So where did these initial density variations, these seeds for all structure, actually come from? The answer lies in one of the most profound and elegant theories in all of cosmology: inflation. To understand it, we have to venture back even further than recombination, to a time so early that our current laws of physics start to break down. We're talking about the first fraction of a second after the Big Bang, around 10 to the power of minus 36 seconds. At this moment, the theory, first proposed by physicist Alan Guth in the 1980s, suggests the universe was filled with a strange high-energy field. And this field had a peculiar property: it generated a repulsive gravitational effect. Instead of pulling things together, this gravity pushed everything apart with unimaginable force. The numbers involved are truly mind-bending. In an interval of time so short it has no comparison in human experience, this inflationary field caused the universe to double in size not once or twice, but perhaps 90 times or more. We're talking about exponential expansion so violent that a region of space smaller than a single subatomic particle was stretched to a size larger than our entire observable universe today. This incredible growth spurt solved several major puzzles in one fell swoop. First, it explains the horizon problem. If you look at the CMB, the temperature is the same in opposite directions of the sky. But in the standard Big Bang model, those two regions could never have been in contact with each other to equalize their temperature. There hadn't been enough time for light or heat to travel between them. Inflation fixes this by saying that these vastly separated regions were indeed once snuggled up right next to each other in that tiny pre-inflationary patch, and the incredible expansion simply pulled them apart. Second, inflation naturally produces a flat universe. Think of it like blowing up a balloon. No matter what the initial wrinkles or curvature were on a tiny patch of the balloon's surface, inflating it to an enormous size makes that patch appear perfectly flat and smooth. This is exactly what we observe in the CMB, but perhaps its most beautiful gift was the creation of those all-important quantum fluctuations. At these incredibly small scales, the universe is a seething, frothing quantum foam where particles and energy flicker in and out of existence due to the Heisenberg uncertainty principle. Inflation took these minuscule quantum jitters, these virtual particles, and stretched them across the cosmos to astronomical sizes. What was once a quantum fluctuation on a subatomic scale became a classical density fluctuation on a galactic scale. These stretched wrinkles became the slight variations in gravitational pull that we now see imprinted as temperature differences in the cosmic microwave background. Without inflation, we would expect the CMB to be far more chaotic and patchy, not exhibiting the specific, statistically smooth pattern that satellites like Planck have so precisely measured. The theory also makes a very specific prediction about the nature of these fluctuations. It says they should be nearly scale invariant. This means that the relative strength of the hot and cold spots should be roughly the same, whether you're looking at large angular scales on the sky or very small ones. It's a cosmic fingerprint that is clearly visible in the power spectrum of the CMB, and it's a stunning success for the inflationary model. However, it's important to note that while inflation is the leading theory, it is not the only game in town. Some physicists propose alternatives, such as bouncing cosmologies where our universe is the result of a previous universe contracting and then bouncing back out, or emergent universe models where the cosmos slowly emerges from a static state. These are fascinating ideas, but so far, none have matched the explanatory power and precise predictive success of inflation when held up against the exquisite data from the CMB. This ancient light acts as the ultimate arbiter, a testing ground for our most fundamental ideas about origin. the continued search for the telltale signs of primordial gravitational waves in the CMB's polarization is the next great test. A detection would be the final, crowning jewel for inflation, solidifying our understanding of the universe's first moment. But if that signal forever eludes us, it may force us to radically rethink our cosmic beginnings, proving that even our most elegant theories must ultimately bow to the evidence written in the sky. Those faint whispers of warmth and cold in the cosmic microwave background are so much more than a snapshot. They are the universe's original architectural blueprint. Think of those slightly denser, warmer patches as tiny gravitational anchors, each one a region where there was just a fraction more mass than its surroundings, began to exert a slightly stronger pull on the matter around it. Over hundreds of millions of years, this gentle tug of gravity started to draw in more and more material, both the ordinary atomic matter we're made of and the mysterious, invisible dark matter. These seeds, imprinted by quantum fluctuations and stretched by inflation, began their slow, inexorable growth. What started as microscopic ripples in the fabric of space-time gradually amplified into vast clouds of gas and dark matter, the proto-galactic fragments that would eventually become the majestic structures we see today. But this cosmic construction project had a silent, invisible foreman, dark matter, because dark matter doesn't interact with light or ordinary matter through any force except gravity. It was immune to the intense radiation pressure that would have otherwise blown the nascent clouds of atomic matter apart. This allowed dark matter to collapse first, forming massive, invisible halos that acted as gravitational wells, a kind of cosmic scaffolding. Once these stable dark matter structures were in place, the ordinary matter, the atoms that would eventually light up as stars, could then flow into these gravitational basins. It's a profound partnership. Without the dark matter providing this stable foundation, the gravitational pull from those initial density variations might not have been strong enough to overcome the universe's rapid expansion, and galaxies might never have formed at all. The ordinary matter simply followed the dark matter's lead, condensing and cooling within these halos to ignite the first stars and illuminate the cosmic dawn. We can actually witness this entire process unfold, not in real time, but through the power of supercomputer simulations. Cosmologists take the precise map of the CMB's fluctuations, the exact pattern and amplitude of those hot and cold spots from the Planck satellite, and use it as the initial conditions for their models. They feed in the known ingredients, the amounts of dark matter, dark energy, and ordinary matter that the CMB itself helped to measure. Then they let the simulation run, applying the laws of physics and gravity to watch 13.8 billion years of cosmic evolution play out in a matter of weeks. The result is nothing short of breathtaking. These simulations show a universe that begins almost perfectly smooth, then gradually weaves itself into an intricate cosmic web, a vast, sponge-like structure of long, dark filaments of dark matter connecting enormous dense clusters of galaxies, all surrounding immense empty voids. And when we compare these simulated universes to the actual large-scale structure we observe with galaxy surveys, the match is stunningly accurate. It's a powerful validation that we truly understand the story, from the first quantum whisper to the grand celestial cities we see today. This entire narrative is elegantly encoded within the acoustic peaks of the CMB's power spectrum. The precise scale of the first peak told us the universe is flat, which dictates how gravity works over vast distances. The height of the second peak gave us a precise measurement of the density of ordinary matter, telling us exactly how much star-making material was available. And the third peak, influenced by the dark matter, revealed how much gravitational scaffolding was present to pull it all together. The CMB doesn't just show us the seeds, It tells us the exact recipe and the rules of the game, allowing us to predict with remarkable confidence how those seeds would grow. It forges an unbreakable link between the physics of the infinitesimally small quantum world and the grandest structures in the cosmos, a connection that spans nearly 14 billion years of history. But if dark matter provided the cosmic scaffolding, what force is directing the overall construction project, shaping the fate of the entire universe? This is where the story takes its most mysterious turn, and once again, the cosmic microwave background provides our most crucial clues. The universe isn't just expanding, that expansion is accelerating, getting faster and faster over time. Something is actively working against gravity's pull, and we call this something dark energy. The CMB allows us to not only detect its presence, but to measure its strength with astonishing precision. One of the key ways it does this is through a subtle, mind-bending phenomenon known as the integrated Sachs-Wolf effect. To understand this, picture a photon from the CMB, a particle of that ancient light, traveling for billions of years across the vast, empty voids and through the immense clusters of galaxies that make up the cosmic web. As it approaches a massive structure like a supercluster of galaxies, it must climb out of its deep gravitational well. In a universe that is decelerating its expansion, the photon would lose energy on the way in and regain exactly the same amount on the way out, leaving its total energy unchanged. However, in our universe where dark energy is causing the expansion to accelerate, the gravitational well itself is actually becoming shallower while the photon is still traveling through it. This means the photon doesn't have to work quite as hard to climb back out. It loses a little less energy than it gained on the way in. The net result is a very slight boost in the photon's energy, which for a CMB photon translates to a tiny, specific warming of its temperature. Conversely, when a photon travels through a large, empty void where gravity is weaker, the effect works in reverse, leading to a slight cooling. By meticulously mapping these specific, subtle temperature shifts in the CMB against the known large-scale structure of the modern universe, cosmologists found the direct, smoking gun signature of dark energy's influence, a powerful independent confirmation of the acceleration first observed in distant supernova. The data from the Planck satellite took this even further, acting as a cosmic accountant to precisely tally the universe's total energy budget. By analyzing the exact pattern of the acoustic peaks in the CMB's power spectrum, the relative heights and spacing of those harmonic fingerprints, scientists could determine with remarkable certainty what the universe is made of. The results are both humbling and awe-inspiring. All the stars, galaxies, planets, and every single thing we can see or touch accounts for a mere 4.9% of the total content of the cosmos. The mysterious, invisible dark matter, which governs the growth of structure through its gravity, makes up 26.8%, and the dominant force, the enigmatic dark energy that is driving the accelerating expansion and shaping the ultimate fate of everything, constitutes a staggering 68.3%. This isn't a rough estimate. These numbers are known with a precision of better than 1%. The CMB tells us that the universe we see is just the faintest visible shimmer on a deep, dark ocean of unknown components. Furthermore, the CMB provides critical details about the very nature of dark matter itself. The way the gravitational pull of dark matter affected the growth of those primordial sound waves tells us that it must be cold. This doesn't mean it's chilly, but rather that it was moving relatively slowly in the early universe. This coldness was essential for it to clump together efficiently and form the gravitational wells that would eventually attract ordinary matter. This finding strongly supports specific theoretical candidates for what dark matter could be, such as WMAP, weakly interacting massive particles, which are heavy particles that interact only through gravity and the weak nuclear force, or actions, which are extremely light, wave-like particles that could theoretically pervade the universe. The CMB data effectively rules out hot dark matter models, where the particles would have been moving close to the speed of light and would have prevented small-scale structures from forming. So, while we still haven't directly detected a dark matter particle, the cosmic microwave background has already told us a tremendous amount about its behavior and its absolutely pivotal role in building the universe we inhabit. It serves as our single most important Rosetta Stone, allowing us to decipher the hidden language of the cosmos and read the story of its invisible ingredients, a story where the known world is a mere footnote to the profound and dominant mysteries of the dark universe. But the true power of the cosmic microwave background isn't just in the story it tells on its own. It's in how that story perfectly harmonizes with the tales told by other, completely independent cosmic messengers. This cross-checking, known in cosmology as the pursuit of concordance, is what transforms a good theory into an unshakable pillar of our understanding. It's the scientific equivalent of getting the same answer to a complex math problem using 3 different calculators. It gives you immense confidence that you've got it right. The CMB, a snapshot of the universe at 380,000 years old, provides the initial conditions. But to see how the story plays out, we need to look at the universe at different ages, and that's where other probes come in. Take Type 1, a supernova, for example. These are spectacular stellar explosions that all reach roughly the same peak brightness, making them what astronomers call standard candles. By measuring how bright they appear to us here on Earth, we can calculate their distance with remarkable accuracy. In the late 1990s, 2 separate teams were using these supernovae to measure the expansion rate of the universe, expecting to find that the gravitational pull of all the matter in the cosmos was gradually slowing it down. To their astonishment, they found the opposite. The most distant supernovae were fainter than expected, meaning the universe's expansion is actually accelerating. This discovery of dark energy earned a Nobel Prize and completely reshaped cosmology. But a single measurement, no matter how dramatic, requires confirmation. The CMB provided that confirmation in a stunningly different way. The pattern of the acoustic peaks in the CMB is exquisitely sensitive to the amount of dark energy. The data from Planck and WMAP didn't just confirm the existence of dark energy, they precisely measured its abundance, and their number was in beautiful agreement with the supernova results. 2 completely different methods, one looking at the very young universe and one at the relatively recent universe, both pointed to the same bizarre conclusion. The cosmos is dominated by a mysterious force causing it to fly apart faster and faster. Then there's the technique of Barrian acoustic oscillations, or BAO. This is a method that actually uses a fossil imprint from the same primordial sound waves we see in the CMB, but it finds that imprint in the modern universe. Remember those spherical sound waves that were frozen in place at the moment of recombination? They left a specific signature, a preferred distance between galaxies. As the universe evolved, galaxies tended to form more frequently at the distance of that first acoustic peak. It's like the universe has a standard ruler etched into its very fabric. By conducting massive galaxy surveys like the Sloan Digital Sky Survey, astronomers can measure this preferred scale in the distribution of millions of galaxies. They can then use this standard ruler to measure cosmic distances and track how the expansion rate of the universe has changed over billions of years. Once again, the measurements from BAO align perfectly with the predictions derived from the CMB. It's a breathtaking link. The same sound waves that created the hot and cold spots we see in the infant universe also dictated the large-scale structure of the galaxy clusters we see today. This triple agreement between the CMB, supernova, and BAO forms the solid bedrock of our current cosmological model, known as lambda CDM. However, this powerful concordance isn't without its intriguing cracks. The most significant of these is a growing puzzle known as the Hubble tension. The Hubble constant is a number that describes the current expansion rate of the universe. We can measure it in two primary ways. The early universe method uses the exquisitely detailed CMB data from Planck. By assuming the lambda CDM model is correct, scientists can calculate what the expansion rate should be today, and they arrive at a very precise value. The late universe method involves building a cosmic distance ladder, using relatively nearby objects like Cepheid variable stars and those type 1a supernova to measure the expansion rate directly. For years, these two methods, each seemingly bulletproof in its own right, have been yielding results that disagree. The local measurements consistently suggest a universe that is expanding faster than the CMB-based prediction. This isn't a small statistical fluke. The discrepancy now has a high degree of significance. This Hubble tension is so persistent that many cosmologists believe it might not be an error at all, but our first tantalizing hint of new physics beyond our current standard model. Perhaps dark energy isn't constant but evolves over time. Maybe there's an unknown type of neutrino or another exotic particle influencing the expansion. Or it could point to a flaw in our understanding of gravity itself. This tension, born from the powerful act of cross-checking the CMB with other probes, is now one of the most exciting and active frontiers in all of science, proving that even our most successful models are always subject to refinement and revolution. This interdisciplinary approach extends beyond the cosmos and into the realm of the infinitesimally small. The CMB also places constraints on the total mass of neutrinos, the elusive ghost particles that flood the universe. The presence of light, fast-moving neutrinos in the early universe would have suppressed the formation of the very smallest galaxies by streaming out of dense regions and washing out some of the clumpiness. By measuring the precise amount of clustering in the universe, both in the CMB and in galaxy surveys, cosmologists can put an upper limit on the combined mass of all neutrino types. Their findings are in remarkable agreement with constraints from particle physics experiments, which measure neutrino mass differences. Together, they tell us that neutrinos are astonishingly light, yet their collective gravity still played a small but measurable role in shaping the cosmos. This is the ultimate in cross-checking, using the largest possible scale, the entire observable universe, to learn about the properties of some of the smallest known particles. It's a powerful reminder that the story of the cosmos is a single, unified narrative, and by listening to all of its chapters, from the ancient whisper of the CMB to the flash of a dying star, we can piece together a robust, evidence-based history of everything. The relentless pursuit of these cosmic whispers now drives us to build even more powerful listeners, instruments of such breathtaking sensitivity that they promise to either capture the faintest echoes of creation or force us to completely rewrite its opening chapters. Leading this charge are two monumental collaborations: the Simons Observatory, currently under construction in the high, dry Chilean Andes, and its even more ambitious successor, CMB Stage 4 or CMB-S4. These aren't single telescopes in the traditional sense. They are vast arrays, coordinated armies of hundreds of thousands of ultra-sensitive detectors working in concert across multiple small telescopes. Their collective goal is to create the most detailed, noise-free maps of the cosmic microwave background ever conceived, with a precision that feels almost like science fiction. Their primary mission is to finally settle the question of primordial gravitational waves by hunting for their telltale B-mode signature in the polarization of the CMB. To do this, they must achieve a sensitivity that is orders of magnitude greater than any previous experiment. Imagine trying to hear a single, quiet whisper in a crowded, noisy stadium. Previous experiments like Bicep were like having a single, very good microphone. The Simons Observatory and CMB S4 are like deploying a vast network of thousands of microphones, each one more sensitive than the last, all working together to cancel out the roar of the crowd and isolate that one precious sound. This crowd noise is the foreground contamination from our own galaxy, the synchrotron radiation from electrons spiraling in magnetic fields, and the thermal emission from interstellar dust. The key to silencing this interference lies in observing the sky at multiple frequencies simultaneously. Because the galactic foregrounds have a very different spectral signature, they behave differently across various wavelengths than the pristine, blackbody spectrum of the CMB. These multi-frequency observations act like a sophisticated filter, allowing scientists to meticulously subtract the Milky Way's contribution and reveal the pristine cosmological signal beneath. But the ambition of these next-generation observatories extends far beyond just polarization. They will also hunt for subtler, even more elusive signatures imprinted on the ancient light. One of these is spectral distortion. The CMB spectrum is a near-perfect blackbody, a curve so flawless that the COBE satellite's measurement of it was described as a direct glimpse into the Big Bang. But near-perfect leaves room for the extraordinary. Theorists predict there should be tiny, 1 part in a million deviations from this perfection, minuscule wiggles in the spectrum that could be the smoking gun for incredible events in the very early universe. These distortions could have been caused by the explosive energy release from the first primordial black holes evaporating, the decay of exotic unknown particles, or the cosmic friction generated by sound waves in the primordial plasma. Detecting any one of these would open an entirely new window into physics at energies we can only dream of recreating on Earth. Furthermore, these powerful instruments could uncover evidence for other exotic relics like cosmic strings. These are theoretical, one-dimensional defects in the fabric of spacetime, thought to have formed during a phase transition in the universe's infancy, like cracks forming in ice. These unimaginably dense and massive filaments, thinner than a proton but stretching across the entire cosmos, would warp space-time around them as they move. If one passed through our line of sight, it would create a unique, sharp step-like discontinuity in the temperature of the CMB, a crack in the very face of the ancient sky. Finding such a signature would be a direct probe of physics at the grand unification scale. The data from these projects will do more than just go hunting for specific signatures. It will provide a foundational dataset of such immense power that it will refine every single parameter of our cosmological model. It has the potential to resolve the persistent Hubble tension, that nagging discrepancy in the universe's expansion rate, by either confirming a systematic error in local measurements or, far more excitingly, providing overwhelming evidence that the tension is real and points toward new physics, such as a dynamical form of dark energy or interactions within the dark sector. This is not just incremental improvement, it is a leap into a new era of precision cosmology, where the faint afterglow of the Big Bang becomes our most powerful laboratory for understanding the fundamental laws of nature. But to unlock these secrets, scientists first face the Herculean task of cleaning the data, of separating the faint cosmic signal from the overwhelming roar of foreground contamination. So we have this pristine signal from the dawn of time, but to actually hear it, scientists first have to silence a cacophony of modern cosmic noise. The cosmic microwave background is like a faint, ancient melody playing on a radio station that's constantly being drowned out by static from our own galactic neighborhood and other sources. This interference is what cosmologists call foreground contamination, and learning to filter it out has been one of the most critical and technically brilliant challenges in the entire field. This galactic noise comes in several distinct flavors, each with its own signature. First, there's interstellar dust. Tiny grains of silicon and carbon, smaller than a wavelength of light, are peppered throughout the Milky Way. When they're warmed by starlight, they re-emit that energy in the far infrared and microwave parts of the spectrum, creating a diffuse, hazy glow that obscures our view. Then there's what's known as free radiation. This isn't a discount sale. It's the emission from free electrons zipping around in hot, ionized gas near bright stars. As these high-speed electrons pass close to atomic nuclei, they're deflected or braked, releasing a burst of radiation. We also have synchrotron radiation, a powerful signal generated by relativistic electrons spiraling at nearly the speed of light along the magnetic field lines that thread through our galaxy. It's the same basic process that creates the brilliant light from distant quasars, but happening right here in our own cosmic backyard. And the challenge doesn't end with the Milky Way. Beyond our galaxy, there are countless extragalactic radio galaxies and massive galaxy clusters that also emit microwaves, adding another layer of interference to the already complex signal. The key to solving this monumental puzzle lies in one fundamental property: color, or more precisely, frequency. The primordial light of the CMB has a very specific and predictable spectrum, that of a perfect blackbody. This means its intensity across different frequencies follows a beautifully smooth mathematical curve that was set in stone when the universe became transparent. The foreground contaminants, on the other hand, do not. Dust, free radiation, and synchrotron radiation all have what's called a spectral energy distribution. Their brightness changes with frequency in a unique and predictable way. Synchrotron radiation, for instance, is much brighter at lower frequencies and fades away quickly as you look higher. Dust emission does the opposite, becoming brighter at higher frequencies. This difference in behavior is the master key that allows scientists to separate the signals. This is why missions like Planck were so revolutionary. They didn't just look at the sky in one microwave frequency. They observed it simultaneously across 9 different frequency bands, from 30 GHz to 900 GHz. It's the cosmological equivalent of having a sophisticated camera with 9 different color filters instead of just one. By taking a picture of the exact same patch of sky in each of these frequencies, researchers can see how the intensity of the emission changes. The parts of the image that get brighter or dimmer in a specific pattern across the frequencies are the foregrounds. The part that maintains the same consistent blackbody ratio across all frequencies, that's the real prize, the cosmic microwave background. But simply having multi-frequency data isn't enough. You need incredibly advanced statistical tools to perform the separation. This is where complex component separation algorithms come into play. Think of these as the most sophisticated noise-canceling headphones ever conceived, powered by supercomputers. These algorithms are fed the multi-frequency maps and are programmed with the known spectral behaviors of each type of foreground. They then perform a massive, multi-variable statistical fit, essentially asking, what combination of galactic dust, synchrotron radiation, and the CMB itself, when added together, perfectly reproduces the total signal we see in all 9 of these maps? It's a monumental computational task, but the output is a set of clean, separate maps, one that shows the distribution of galactic dust, another for synchrotron emission, and finally, a pristine, cleaned map of the CMB itself, with the veils of our own galaxy pulled aside. The absolute necessity of this process cannot be overstated. Any residual contamination left in the final CMB map, even at a tiny level, can systematically bias our results. If a patch of dust is mistaken for a genuine CMB cold spot, it could lead us to incorrectly calculate the amount of dark matter. If a hint of synchrotron radiation is left in, it could distort the measured polarization and create a false signal that looks like the elusive B modes from inflation. The entire endeavor of precision cosmology hinges on this meticulous cleaning process. The phenomenal success of the Planck mission, which provided our most precise cosmological parameters to date, is a direct testament to decades of improvement in our understanding of these foregrounds and our ability to model and subtract them with breathtaking accuracy. We have effectively learned to erase our own local environment from the picture, to see the ancient forest for the modern trees, revealing a universe far older and more mysterious than our galactic home. Yet for all its stunning success and precise predictive power, our standard model of cosmology is not a perfect, seamless narrative. If you look closely enough at the cosmic microwave background map, past the beautiful statistical agreement and the elegant acoustic peaks, you begin to notice a few faint, strange wrinkles that don't quite fit the story. These are the CMB anomalies, quirky, unexpected features that are statistically unlikely within our current understanding of the universe. They are the loose threads in the cosmic tapestry, and while they might ultimately be explained away as subtle measurement errors or local effects, they also represent the most tantalizing potential cracks in our foundational theories, hints that there might be something profound and entirely new waiting to be discovered. One of the most famous and puzzling of these is a large-scale pattern nicknamed with a touch of dramatic flair, the axis of evil. In a universe that is supposed to be isotropic and homogeneous, meaning it should look the same in every direction with no preferred axis or center, this finding is deeply strange. When scientists analyze the largest-scale temperature fluctuations in the CMB, they appear to be subtly aligned along a particular direction in space. It's as if the universe has a faintly defined equator and poles. This isn't just a visual curiosity, it's a statistical one. The chance of such an alignment occurring randomly in our standard model of cosmology is extremely low, less than 1 in 1,000. It's like rolling a die 100 times and getting a 6 almost every single time. It's not impossible, but it certainly makes you wonder if the die is weighted. This apparent preferred direction challenges a cornerstone principle of modern cosmology, the cosmological principle, which states that the universe should be broadly the same no matter where you are or which way you look. The axis of evil forces us to ask a radical question. Could there be a fundamental direction to the cosmos, a relic of some process that broke perfect symmetry at the very beginning? Then there is the mysterious cold spot. This is a particularly large and unusually cold region in the CMB, located in the constellation Eridanus. It's not just a little bit colder. Its size and temperature deviation make it a significant outlier. In a map that is otherwise statistically Gaussian, meaning its fluctuations are random and evenly distributed, the cold spot stands out like a single, deep, and unexpected crater on an otherwise smooth plane. One compelling explanation is that it might not be a primordial feature at all, but a secondary effect caused by something called the integrated Sachs-Wolf effect. This would occur if the CMB photon passed through an immense cosmic void, a vast underdense region of the universe with far fewer galaxies and less matter than average. As a photon enters such a void, it climbs out of the gravitational well of the surrounding denser regions, which costs it energy and makes it appear slightly cooler. However, extensive galaxy surveys have struggled to find a void large enough and empty enough to explain the profound coldness of this spot. This has led to more exotic proposals. Some theorists suggest it could be the imprint of a cosmic texture. This is a hypothetical defect in the fabric of space-time, a kind of knot that formed during a phase transition in the early universe, much like cracks forming in ice. If one of these textures unraveled, it would have released a tremendous amount of energy, creating a unique signature that could manifest as a large cold spot in the CMB. It's a wild idea, but it's precisely the kind of speculative leap these anomalies inspire. Beyond these two headline grabbers, there are other, subtler curiosities. The CMB shows a curious hemispheric asymmetry. The statistical properties of the fluctuations aren't perfectly uniform across the entire sky. One half of the sky appears to have slightly larger temperature variations than the other. Furthermore, there's a puzzling lack of correlation on the very largest scales. The temperature points that are the farthest apart on the sky don't seem to vary as much as the standard model predicts they should. It's as if the universe is somehow smoother and more connected on its grandest scales than our theories say it has any right to be. So, what are we to make of these ghosts in the data? The most cautious and likely explanation is that they are systematic artifacts, subtle errors introduced by our instruments, or more probably, by the incredibly complex process of foreground subtraction. Perhaps a faint, undetected cloud of galactic dust or an unaccounted-for source of radio interference is creating a pattern that mimics an anomaly. This is why the scientific community treats these features with healthy skepticism. Extraordinary claims require extraordinary evidence, and these anomalies have not yet risen to that level. They are intriguing, not conclusive. However, their persistence is what fuels alternative thinking. For a small group of cosmologists, these anomalies are the first faint whispers of physics beyond our standard model. They could be evidence for non-Gaussianity, a sign that the primordial fluctuations weren't perfectly random as predicted by simple, single-field inflation, but had more complex correlations, pointing towards models like multi-field inflation where multiple inflationary fields interacted. Some have even speculated more radically that these features could be a bruise left from a collision with another universe in the vast multiverse, a cosmic fingerprint from a realm beyond our own. While this remains highly speculative, it demonstrates how these puzzling data points act as a powerful engine for innovation, driving theorists to dream up models they might never have otherwise considered. They are the unanswered questions that keep cosmology alive and exciting, a reminder that for all we have learned, the universe still holds profound mysteries written in its oldest light. While the cosmic microwave background has already reshaped our understanding of the universe's history and composition, it may hold an even deeper layer of secrets, clues that could guide us toward a theory of everything. The greatest challenge in modern physics is unifying Einstein's theory of general relativity, which governs the immense scale of galaxies and the cosmos, with quantum mechanics, the bizarre and probabilistic rules that dominate the subatomic world. These two pillars of physics are spectacularly successful in their own domains, but they are fundamentally incompatible. Bridging this divide requires a theory of quantum gravity, and the CMB, as our earliest and most pristine physical record, offers a rare observational window into this theoretical frontier. Consider the moment of inflation, that incredible burst of exponential expansion. According to many models, the quantum fluctuations that were stretched to cosmic size originated at energies far beyond the Planck scale, a realm where the quantum nature of spacetime itself becomes apparent. This is the domain of trans-Planckian physics, a regime where our current laws break down and where theories like string theory or loop quantum gravity must take over. These theories make specific, if incredibly subtle, predictions about how this quantum origin might have left its mark on the CMB. For instance, the process might have imprinted a slight deviation from perfect randomness in the distribution of the hot and cold spots, a feature known as non-Gaussianity. It's a bit like expecting the static on an old television to be completely random, but upon incredibly careful analysis, finding faint, repeating patterns hidden within the noise. The current data from Planck show the fluctuations are Gaussian to a very high degree, but future experiments like CMB S4 will search for these non-Gaussian fingerprints with vastly improved sensitivity, potentially revealing the quantum grain of spacetime. Another fascinating possibility lies in the very shape of space. Our standard model assumes the simplest topology, that the universe is infinite and flat. But what if its overall connectivity is more complex? Some theories allow for a finite universe with a non-trivial topology, meaning space could be folded in on itself in a multiply-connected way. Imagine the universe being like a video game world where if you travel far enough in one direction, you eventually return to your starting point from the opposite side. Such a geometry would leave a specific, correlated pattern of matching circles in the CMB pairs of cold spots that are actually the same physical region of the early universe, seen from two different directions. Scientists have searched for these telltale circles in the Planck data, but so far none have been found, suggesting that if the universe is multiply-connected, the identification scale must be larger than the observable horizon. The most speculative yet thrilling ideas involve signatures of higher dimensions. String theory, for example, proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings existing in 10 or 11 dimensions. The extra dimensions are curled up or compactified to a size too small for us to perceive directly. However, the dynamics of this compactification in the very early universe could have influenced the spectrum of gravitational waves generated during inflation. This would alter the expected strength of the primordial B-mode polarization signal in a specific way. Detecting a B-mode signal that is stronger or weaker than the simplest models of inflation predict could be our first indirect evidence for these hidden dimensions, a cosmic hint that our reality is far more expansive than it appears. Currently, the exquisite data from Planck and other observatories show no strong evidence for these exotic ideas. The universe, at least within the observable CMB, appears reassuringly simple and well described by the standard model of cosmology. But this lack of evidence is in itself profoundly valuable. It places incredibly tight constraints on these advanced theories, forcing theorists to refine their models and discard those that are incompatible with the empirical evidence. This is the beautiful, iterative dance of science at its best. Wild, imaginative ideas from the farthest reaches of theoretical physics are brought before the sober judge of observational data. The CMB acts as that impartial judge, a silent witness from the beginning of time that patiently waits for us to ask the right questions with ever-increasing precision. The next generation of experiments will continue this dialogue, probing the CMB for the faintest whispers of quantum spacetime foam, cosmic strings, or other relics that could finally illuminate the path to a unified theory of physics. This idea of apparent fine-tuning leads us directly to one of the most profound and debated concepts in modern cosmology, the anthropic principle. In its simplest form, the anthropic principle observes that the universe we observe must be compatible with the existence of observers like us. It seems like a tautology, a simple statement of the obvious, but when applied to the precise numbers gleaned from the CMB, it becomes a powerful, and to some, a deeply unsettling explanatory tool. The constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant do not seem to be predicted by any fundamental theory. They appear to be arbitrary, Yet, if any one of them were even slightly different, the universe as we know it would not exist. If the density fluctuations imprinted on the CMB were significantly weaker, gravity would never have been able to overcome the expansion of the universe to clump matter into galaxies, stars, or planets. There would be no structures at all, just a cold, dark, and ever-diluting haze of atoms. Conversely, if those initial fluctuations were too strong, matter would have collapsed into a nightmare landscape of voracious black holes long before life could ever emerge, a universe far too violent and short-lived for any complexity to arise. The value of the cosmological constant, or dark energy, is perhaps the most striking example of this fine-tuning. As measured by Planck, it is astoundingly small, but crucially not zero. If it were significantly larger and positive, the universe would have ripped itself apart before galaxies could form. If it were negative, the cosmos would have recollapsed into a big crunch eons ago. The fact that we exist in a universe where this value is so perfectly balanced to allow for both structure formation and long-term expansion seems, to many, like a cosmic coincidence of unbelievable luck. This is where the anthropic principle moves from an observation into a potential explanation. Rather than searching for a fundamental law that dictates these perfect values, some physicists and philosophers suggest that there may be no deeper reason. In this view, our universe is simply one that has the right conditions for life, and we are here to observe it precisely because those conditions were met. We are, in a sense, selecting ourselves out of a vast array of possibilities. This line of thinking finds a natural, and for some, a comfortable, home within the framework of the multiverse. The theory of eternal inflation, a popular extension of the basic inflationary model, suggests that our Big Bang was not a unique event. Instead, inflation may be a perpetual process, giving birth to an endless multiverse, a vast and perhaps infinite ensemble of separate, disconnected universes, often called pocket universes. In each of these universes, the fundamental constants, the laws of physics, and even the number of spatial dimensions could be randomly different, set by the random nature of the quantum processes that spawned them. In the overwhelming majority of these universes, the parameters would be wrong for life. They would be stillborn or collapse instantly or fly apart too quickly. But in a tiny, unimaginably small fraction of them, the dice would roll just right. The cosmological constant would be small, the density fluctuations would be perfect, and life would have a chance to emerge. We, of course, find ourselves in one of those exceptionally rare, bio-friendly universes. Our cosmic home isn't special, it's just lucky. The CMB, therefore, is more than a picture of our beginning. It is a local weather report from our particular hospitable pocket in a much larger and largely inhospitable multiverse. This idea is without question controversial. Critics argue that the multiverse is an untestable, metaphysical concept that effectively gives up on the traditional goal of physics to find a unique, fundamental theory that explains why our universe is the way it is. It replaces a law of nature with a statistical accident. Proponents counter that it is a natural prediction of our best theories of the early universe, and that, indirectly, the specific values we measure in the CMB values that seem so finely tuned for life are themselves the evidence. The debate straddles the line between hard science and deep philosophy, forcing us to confront questions about the very nature of reality and our place within it. The cosmic microwave background, a relic of the most violent physical event, has become the centerpiece of a conversation about existence, probability, and the possibility that our entire universe is just one fortunate island in an infinite cosmic ocean. Right now, the cosmic microwave background is a cold whisper, a faint signal we can detect with our most sophisticated technology, But this whisper is not permanent, it is fading. The relentless expansion of the universe, driven by the mysterious force of dark energy, is not just pushing galaxies apart, it is actively stretching the very fabric of space-time itself. And as space stretches, the wavelength of light traveling through it gets pulled longer. This is the phenomenon of redshift, and it is slowly but surely transforming the CMB before our very eyes, or more accurately, before our telescopes. Over timescales that are almost impossible to comprehend, this process will continue unabated. The CMB's photons, which today are in the microwave part of the spectrum, will redshift further and further into longer and longer radio waves. Their energy will diminish and their signal will grow fainter. In about 100 billion years, the wavelength of this ancient light will have stretched so much that it will be measured in meters, not centimeters, and its signal will be buried deep within the radio noise of our own Milky Way galaxy, impossible to distinguish from the background chatter of celestial objects. Looking even further into the abyss of time, trillions of years from now, the fate of the CMB becomes a profound lesson in cosmic ephemerality. For any astronomers, be they human or whatever form intelligence might take in that distant era, the sky will present a radically different picture. The CMB will have redshifted so dramatically that its photons will have wavelengths larger than the observable universe itself. In practical terms, this means the signal will have effectively vanished, dissipated into nothingness. The last tangible remnant of the Big Bang will be gone. The night sky, which today glows with this ancient light in every direction, will appear utterly dark to them in these radio frequencies. All the galaxies beyond our local gravitational bound group will have been pushed so far away by the expansion that their light can no longer reach us. The universe will have expanded faster than the speed of light can bridge the gap. This future cosmos will be a lonely, isolated place, with a dark, empty sky offering no clue to its explosive and energetic beginning. It will be the visual manifestation of the heat death of the universe, a state of maximum entropy where the cosmos is a cold, thin, and ever-diluting soup of particles. Yet, even when the last photon of the CMB has faded into undetectability, its legacy will be permanently etched into the architecture of the cosmos. The patterns of density it revealed, those tiny fluctuations that were the blueprints for all structure, will have long since finished their work. The grand cosmic web of galaxies, clusters, and superclusters we see today is the direct physical manifestation of those ancient seeds. While the light that revealed them will be gone, the structures themselves will remain, frozen in their final configurations, a silent, monumental monument to the beginning. For a future civilization that arises in this far-flung era, piecing together the history of the universe will be an unimaginably difficult task. Without the CMB's detailed snapshot, they would lack the very first page of the cosmic story. They might gaze upon the majestic but static architecture of the galaxies and have no way of knowing it all began in a hot, dense state. This realization makes our current epoch incredibly special. We live in a unique golden age of cosmology, a brief sliver of cosmic time just a few centuries wide, where the afterglow of creation is still detectable and the universe's story is still readable. We are temporary witnesses to a permanent record, and that fills our scientific pursuit with a deep and poignant significance. But perhaps one of the most powerful ways the story of the cosmic microwave background has been shared is through the rise of citizen science. While the intricate data analysis of the CMB itself requires specialized expertise, projects like Galaxy Zoo have brilliantly captured the public's imagination by inviting them to participate in related cosmological detective work. By asking volunteers to classify the shapes of millions of galaxies online, these initiatives not only produce valuable scientific data, but also create a direct personal connection to the larger narrative of structure formation, a story that begins with those tiny fluctuations in the CMB. This collaborative spirit, where anyone with an internet connection can contribute to real science, demystifies the research process and transforms abstract concepts into a shared human endeavor. It reinforces the beautiful idea that understanding the universe isn't just for those with PhDs. It's a fundamental part of our curiosity as a species. Ultimately, this drive to share these profound discoveries stems from a deep-seated recognition that this knowledge belongs to everyone. The story of the CMB is more than a tale of satellites and equations. It's a testament to human collaboration, perseverance, and our innate desire to understand our place in the cosmos. By bringing these concepts out of the ivory tower and into the public square, scientists do more than just educate. They inspire awe and wonder. They invite the next generation of explorers, engineers, and dreamers to look up at the night sky and see not just points of light, but a historical archive, a cosmic fossil record waiting to be read. This public engagement ensures that the journey of cosmic discovery continues, fueled by the collective curiosity of all humankind. Gazing at the map of the cosmic microwave background is a profoundly humbling experience. It is a direct view of the universe at 380,000 years old, a snapshot from a time when our planet, our sun, and even our galaxy did not exist. It reveals a cosmos of almost unimaginable scale, both in space and in time, stretching over 13 billion years into the past and encompassing billions of light years in every direction. In this vast tapestry, humanity occupies a vanishingly small moment. Our entire recorded history is less than a blink of an eye on this cosmic timescale, and our planet is a tiny, fragile speck orbiting an average star in the outskirts of an unremarkable galaxy. This perspective doesn't diminish our achievements, but it radically recontextualizes them. We are not the center of the universe. We are a recent, conscious flicker within it, gifted with the extraordinary ability to look back and comprehend our own origins. This realization inevitably forces us to confront deep philosophical questions about existence itself. If the fundamental constants and initial conditions revealed by the CMB were so exquisitely fine-tuned to allow for galaxies, stars, planets, and ultimately life, what does that mean? Are we the product of an unimaginably fortunate cosmic accident, a statistical outlier in a multiverse of failed universes? Or does our ability to observe and understand these precise laws suggest a deeper connection between consciousness and the cosmos? Furthermore, the sheer scale of the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, makes the existence of other civilizations seem not just possible, but probable. The CMB is a universal constant. That same ancient light fills the skies of every potential world, meaning any other technological civilization would have the same primordial Rosetta Stone to decode. This shared cosmic heritage could one day provide a common foundation for communication, a universal science that transcends any biological difference. Understanding our story, from the quantum fluctuations in the first instant to the complex beings we are today, also fosters a powerful sense of cosmic stewardship. The same laws of physics that govern the expansion of the universe and the life cycle of stars also operate here on Earth. We are made of stardust, forged in the hearts of long-dead stars that seeded the cosmos with the heavy elements necessary for life. This knowledge can inspire a greater sense of global cooperation and a responsibility to protect our tiny, pale blue dot, the only home we have ever known. The petty divisions of borders, politics, and ideology fade when viewed against the backdrop of the cosmic microwave background. We are all, quite literally, made from the same ancient ashes of the Big Bang, living on a fragile world adrift in a vast and mostly empty cosmos. This perspective encourages a shift from a mindset of narrow nationalism to one of a shared human and potentially universal destiny. While deciphering the CMB may not lead to a new consumer gadget or directly solve our immediate earthly problems, its value is immeasurable in a different currency, that of cultural enrichment and pure, unadulterated awe. This research pushes the very boundaries of human knowledge and technological capability. The struggle to measure a signal 1/1,000,000th of a degree above absolute zero drives innovation in sensors, materials, and computing, with spin-offs that often find unexpected applications in medicine and communications. But more importantly, it answers a fundamental human drive that we have had since we first looked up at the night sky: the need to understand where we came from and how we fit into the grand scheme of things. It is a modern-day creation story, but one built on evidence, collaboration, and reason. It provides a narrative that can inspire generations of scientists, engineers, artists, and philosophers, enriching our collective culture with a deeper, more accurate, and more magnificent view of reality. The ability to know our cosmic address from a specific planet to the afterglow of the universe itself is one of the greatest achievements of the human intellect, a story that belongs to all of us. Fortunately, the journey to understand the cosmic microwave background isn't a path you have to walk alone. It's a vibrant, collaborative expedition, and there are more ways than ever to join the conversation, whether you're an aspiring cosmologist or simply captivated by the universe's oldest story. For those who want to dive straight into the raw, cutting edge of discovery, the best place to start is the arXiv preprint server, pronounced archive, this open-access website at arXiv.org is where physicists from around the world post their research papers before they undergo formal peer review. It's the unfiltered pulse of the scientific community. You can search for papers on topics like CMB polarization or B-mode constraints and read the conclusions and abstracts to get a direct sense of the latest debates and breakthroughs, all for free. It can be technical, but it offers an unparalleled, real-time window into how science is actually done. For more curated and digestible mission updates, the websites of NASA and the European Space Agency, ESA, are incredible treasure troves. These are the public portals for the projects that have given us our most profound cosmic insights. You can explore the vast public archives of the Planck satellite, downloading its all-sky maps and even the raw data if you're feeling adventurous. These sites are filled with press releases written for a general audience, stunning visualizations, detailed explainers on the technology behind the telescopes, and interviews with the scientists themselves. Following their social media channels is like having a backstage pass to the greatest show in the cosmos, offering glimpses of engineers assembling new detectors or researchers celebrating a successful observing run at the South Pole. If you prefer to learn on the go, the world of podcasts brings the universe directly to your ears. Shows like Star Talk with Neil deGrasse Tyson masterfully blend science and pop culture with humor and accessibility, often featuring cosmologists who work on the CMB. The Universe Today podcast, hosted by Fraser Cain, offers deep-dive interviews and news rounds that consistently cover new developments in cosmology with clarity and enthusiasm. For a more academic but still approachable tone, many leading universities and research institutes, like the Kavli Institute for Cosmology, produce their own lecture series and podcasts featuring the very researchers who are writing the textbooks. And you don't need to enroll in a PhD program to get a world-class education in this field. Platforms like Coursera and edX host free online courses from top universities on cosmology and astrophysics. You can find introductory courses that build your knowledge from the ground up, all the way to specialized classes that delve into the mathematics of inflation and the statistics of CMB data analysis. These courses allow you to learn at your own pace, often with interactive exercises and discussion forums where you can connect with fellow enthusiasts from across the globe. For a more hands-on approach, local astronomy clubs are a fantastic resource. While they often focus on night sky observing, many clubs have special interest groups in cosmology and host guest lectures from local university professors. This is a wonderful way to meet people who share your passion and to ask questions in a friendly, informal setting. Furthermore, anyone can become an advocate for this profound research by supporting public funding for science through organizations that lobby for strong investment in agencies like NASA and the National Science Foundation, which are the lifeblood of these grand exploratory projects. Engaging with this multifaceted community, from reading preprints to listening to podcasts, transforms the awe of the cosmos from a solitary feeling into a shared, living dialogue, ensuring that the wonder of discovery is a flame that gets passed on to the next generation of cosmic explorers. For all we have learned from the cosmic microwave background, this ancient light is far from having given up all its secrets. In fact, the most profound mysteries of our universe are still encoded within its subtle patterns, waiting for the next generation of experiments and theorists to crack their code. The CMB has provided us with a stunningly precise recipe for the cosmos, but it has also handed us a list of ingredients: dark matter, dark energy, inflation, that we fundamentally do not understand. We know these components exist and dominate the cosmic budget, but their true nature remains one of the greatest puzzles in all of science. The hunt for what dark matter actually is, whether it's a yet-to-be-discovered particle like a WMAP or an action, or something even more exotic, is a primary driver of physics. Similarly, the identity of dark energy, the force causing the universe's expansion to accelerate, is completely unknown. Is it a cosmological constant, a static energy inherent to the vacuum of space itself, or is it a dynamic field that has changed over the lifetime of the cosmos? The answer to this question will determine the ultimate fate of everything. Then there is the persistent and growing Hubble tension. This isn't just a minor statistical discrepancy, it's a crack in the foundation of our standard model of cosmology. When we use the pristine conditions of the early universe, as recorded by the Planck satellite, to predict the current expansion rate, we get one very precise number. But when astronomers use direct measurements of nearby stars and galaxies to measure that expansion rate today, they consistently get a larger, faster value. This isn't an error that has gone away with better data. It has only become more significant. This tension suggests that there might be something missing from our model, perhaps a new type of neutrino, a previously unknown interaction in the dark sector, or even that dark energy is not constant but evolving. Resolving this conflict is perhaps the most urgent task in cosmology, as it could be our first genuine clue to physics beyond our current understanding. And of course, the ghost of primordial gravitational waves continues to haunt the field. The detection of the telltale B-mode polarization pattern would be a direct window into the inflationary epoch, confirming not only that it happened but also revealing the tremendous energy scale at which it occurred. The fact that this signal has so far eluded us despite Herculean efforts is itself a profound piece of information. It is already forcing theorists to refine their models of inflation, moving away from the simplest versions and towards more complex multi-field scenarios. Each null result pushes the energy scale of inflation lower, constraining our ideas about how the universe began. Furthermore, the strange anomalies in the CMB, like the large cold spot and the puzzling hemispheric asymmetry, linger without definitive explanation. While they could still be statistical flukes or subtle systematic errors, they continue to inspire more radical ideas, from cosmic textures to collisions with other universes in a vast multiverse. The incredible potential of future CMB experiments lies in their ability to transform these unanswered questions from philosophical musings into empirical data. Projects like the Simons Observatory and CMB-S4 will survey the sky with such breathtaking sensitivity that they could finally detect the faint swirl of primordial B modes, or they could rule out entire classes of inflationary models, sending theorists back to the drawing board. They will measure the CMB's polarization and temperature with such precision that they could resolve the Hubble tension, revealing whether it is a measurement error or a gateway to new physics. They might even detect the spectral distortions that would be the smoking gun for incredibly energetic processes in the very early universe, such as the decay of exotic particles or the evaporation of primordial black holes. The data from these observatories won't just provide answers, they will undoubtedly reveal new, unexpected phenomena that we haven't even thought to ask about yet. This is the thrilling nature of fundamental science. The universe is always more imaginative than we are. This pursuit also highlights a beautiful truth about cosmology. No single messenger can tell the whole story. The cosmic microwave background is our most powerful relic, but it is not our only one. To build a complete history of the universe, we must cross-correlate its story with other, equally ancient fossils. This is where the interconnections become so vital. For instance, the cosmic neutrino background is a predicted sea of low-energy neutrinos that decoupled from matter even earlier than the CMB photons, just 1 second after the Big Bang. While we have not yet directly detected these faint particles, we know they must exist, and we can see their gravitational influence. The presence of these neutrinos subtly suppressed the formation of the smallest galaxies and left a specific imprint on the clustering of matter we see in the CMB and in the large-scale structure of the universe today. Detecting this neutrino background directly is a monumental technical challenge, but it would provide a snapshot of the universe that is 1,000,000 times younger than the CMB, offering a unique glimpse into an even more primordial era. Similarly, the search for a stochastic gravitational wave background connects directly to the story told by the CMB. The primordial B modes we search for in the CMB are the imprint of gravitational waves on the photons from the dawn of time. But those same gravitational waves should still be washing through the universe today as a faint background hum. Ground-based interferometers like LIGO and Virgo detect the high-frequency ripples from cataclysmic events like black hole mergers, but a future space-based observatory like LISA could be sensitive enough to detect the low-frequency hum of these primordial waves directly. Finding this background would be the ultimate confirmation of the inflationary paradigm, a complementary signal to the CMB that would tell the same story of the universe's violent birth through a completely different messenger. By combining the evidence from light, neutrinos, and gravitational waves, we are not just reading a single historical text, we are cross-referencing multiple independent accounts of the same event, building a robust and undeniable narrative of our cosmic origin. This multi-messenger approach is the future of cosmology, and the CMB will remain its foundational pillar for decades to come. While the cosmic microwave background is our most detailed fossil from the early universe, it is far from the only one. Imagine trying to reconstruct the complete history of an ancient civilization by finding just one scroll. You would learn a great deal, but to truly understand, you would need to cross-reference it with other artifacts, pottery, coins, and other documents. Cosmology is no different. To build a complete and verified history of the cosmos, we need multiple independent messengers, and two of the most crucial are the cosmic neutrino background and the primordial gravitational wave background. These are the other key texts in our cosmic library, and they tell complementary parts of the same incredible story. The first of these, the cosmic neutrino background, is arguably even more ancient than the CMB. While the CMB photons were set free 380,000 years after the Big Bang, neutrinos decoupled from matter a mere 1 second after the beginning. At that unimaginably early moment, the universe was so hot and dense that even these ghostly, barely interacting particles were trapped in the hot plasma soup. But as the cosmos expanded and cooled, it suddenly became transparent to neutrinos. They streamed out in all directions, and they have been traveling virtually unchanged for the last 13.8 billion years. This means there is a sea of these primordial neutrinos flooding the universe today, a cosmic neutrino background with a predicted temperature of just 1.95 degrees above absolute zero, even colder than the CMB. We have not yet directly detected this background because these neutrinos have incredibly low energy, making them a monumental technical challenge to capture. But we know they are there because we can see their gravitational fingerprint on the universe we observe today. Their influence is written in the large-scale structure and, remarkably, in the CMB itself. The presence of this sea of neutrinos acted like a subtle drag on the formation of cosmic structure. Neutrinos are extremely light and fast-moving, and this high speed meant they could stream out of the slightly denser regions that were trying to collapse under gravity. This streaming effect washed out some of the clumpiness, suppressing the formation of the very smallest galaxies. We can see this effect in the precise statistical distribution of galaxies in modern sky surveys. There is a specific cutoff in the clustering on small scales that matches the predicted influence of neutrino-free streaming. Furthermore, the presence of these neutrinos altered the precise timing and amplitude of the acoustic oscillations in the primordial plasma, leaving a specific, calculable imprint on the CMB power spectrum. By analyzing the CMB data from Planck, cosmologists have actually placed an upper limit on the total mass of all neutrino species, a finding that aligns beautifully with constraints from particle physics experiments. It's a stunning example of using the largest scales in the universe to learn about the properties of some of the smallest known particles. The second cosmic messenger is even more ethereal, a stochastic background of primordial gravitational waves. These are not the waves from colliding black holes detected by LIGO, but something far more profound. They are the literal ripples in the fabric of spacetime itself, theorized to have been generated by the violent quantum energy processes of the inflationary epoch. This background would be a faint, persistent hum resonating throughout the cosmos, a fossil vibration from the universe's first moment. Its detection would be the ultimate confirmation of inflation and would allow us to measure the energy scale at which it occurred. And just like the neutrino background, its story is deeply intertwined with the CMB. The most promising way to detect these waves is by looking for their unique signature, the B-mode polarization patterns, in the CMB, as we've discussed. But there is another, more direct method on the horizon. Future space-based observatories like the proposed Laser Interferometer Space Antenna, or LISA, are designed to detect low-frequency gravitational waves. While LISA will be superb at finding waves from merging supermassive black holes, it could also, over a long enough observation time, piece together the faint, all-pervasive hum of the primordial gravitational wave background. Finding this signal would be like switching from reading the history of the universe to listening to its soundtrack. It would provide a completely independent channel of information, one that is immune to the interference of light or dust that can obscure electromagnetic signals like the CMB. A detection by LISA would perfectly complement the story told by the CMB, cross-checking the narrative and providing a multi-messenger view of the universe's birth. This integrative approach, combining light, neutrinos, and gravitational waves, is the undeniable future of cosmology. It transforms the field from relying on a single, albeit spectacular, witness to having multiple, independent accounts of the same event, allowing us to build a robust, verified, and breathtakingly complete history of everything. This relentless pursuit of the universe's faintest whispers does more than just satisfy our cosmic curiosity. It forces us to push the very boundaries of engineering and computing, creating technological breakthroughs that ripple out into society in the most unexpected ways. The extreme challenge of measuring temperature variations of a few millionths of a degree while filtering out a cacophony of galactic noise demands instruments of almost unimaginable sensitivity. To meet this challenge, scientists and engineers have had to become pioneers, inventing new technologies that are now finding life-saving applications far from the mountaintops and satellites where they were born. One of the most significant breakthroughs to emerge from this field is the development of the Transition Edge Sensor, or TESS. Imagine a thermometer so sensitive it could detect the heat of a single photon. That's essentially what a TES is. These microscopic devices are made from special superconducting materials kept at a fantastically cold temperature, right on the knife edge between their superconducting and normal states. The slightest amount of energy, like the minuscule heat from a single microwave photon from the CMB, is enough to bump it out of superconductivity, causing a measurable change in its electrical resistance. This incredible sensitivity is what allows telescopes like the Atacama Cosmology telescope and those in the Simons Observatory to map the CMB's subtle polarization. But the utility of this technology doesn't end in Chile. That same exquisite sensitivity to tiny energy deposits makes TS detectors perfect for a completely different field, medical imaging. They are now being integrated into new generations of X-ray and gamma-ray spectrometers. In a medical scanner, this means being able to distinguish between different tissue types with far greater clarity, or using a lower dose of radiation to achieve a clearer image, making diagnostics both safer and more accurate. This direct path from measuring the birth of the universe to improving human health is a powerful testament to the unpredictable benefits of fundamental research. Alongside these incredible sensors, the quest to hear the cosmic signal required a revolution in amplification. The faint microwaves from the early universe are easily drowned out by the inherent electronic noise of the amplifiers themselves. To solve this, CMB researchers helped drive the development of ultra-low noise amplifiers, particularly based on a technology called HEMT, or High Electron Mobility Transistors. These amplifiers are so quiet and efficient that they can boost a vanishingly weak signal from space without adding significant distortion of their own. This technology, refined in labs focused on the cosmos, is now absolutely vital to the modern world. It forms the backbone of the hardware in every cell phone tower, enabling the clear signal transmission that connects our global society. It's also fundamental to the development of quantum computers, where maintaining the integrity of incredibly fragile quantum states requires amplifiers that can read signals without destroying them. The same tech that listens to the Big Bang is helping to build the next generation of computational power, but the innovation isn't just in the hardware, it's in the software and the very way we think about data. A modern CMB experiment doesn't produce a simple photograph. It generates a colossal flood of raw data, petabytes of information from thousands of detectors scanning the sky across multiple frequencies. Making sense of this requires incredibly sophisticated data analysis techniques. Cosmologists have become masters of advanced statistical methods, machine learning algorithms, and component separation, the art of untangling multiple overlapping signals. The algorithms developed to isolate the CMB from galactic dust are now being adapted for use in entirely different fields. For instance, similar techniques are used in machine learning to clean and classify large datasets, in finance to identify subtle market trends buried in noise, and in genomics to unravel complex sequences of DNA. The challenge of finding a pattern in a universe of chaos has honed tools that are now applied to some of our most pressing earthly problems. This story of unintended benefits is a powerful reminder that you cannot always predict the return on investment for curiosity-driven science. The scientists trying to detect primordial gravitational waves weren't trying to invent better medical scanners. They were focused on a profound question about the nature of reality. Yet, in striving to answer that question, they were forced to innovate at the very edges of possibility, and those innovations inevitably spilled over, creating new industries and improving lives. It demonstrates that funding fundamental research isn't a luxury. It's an investment in a future of unforeseen technological riches, a catalyst that drives progress across the entire spectrum of human endeavor. The tools we build to comprehend the cosmos have a remarkable habit of helping us better understand ourselves and our world. If your curiosity has been sparked by the story of the cosmic microwave background and you're eager to dive even deeper, you are in for a treat, because there is a wealth of incredible resources waiting for you, designed for every level of interest. For a truly foundational read, you can't go wrong with Steven Weinberg's classic book, The First 3 Minutes. This isn't just a historical text. It's a beautifully written narrative that walks you through the physics of the early universe with a clarity and passion that remains unmatched, written by a Nobel laureate who helped shape our modern understanding. If you're looking for a more visual and panoramic tour of cosmology, Welcome to the Universe by Neil deGrasse Tyson, Michael Strauss, and J. Richard Gott is a fantastic choice. It's an immersive and surprisingly deep journey that starts with our solar system and expands all the way out to the cosmic horizons, with clear explanations of the CMB's role in the grand scheme of things. For those who love to sit back and watch the story unfold on screen, several documentaries bring this cosmic drama to life with stunning visuals. The Nova mini-series The Fabric of the Cosmos, based on Brian Greene's book, dedicates significant time to unpacking the concepts of inflation and the afterglow of the Big Bang, using state-of-the-art graphics to make abstract ideas tangible. Another excellent visual journey is Inside the Milky Way, which, while focused on our galaxy, does a beautiful job of contextualizing our local cosmic neighborhood within the larger history revealed by the CMB. When you're ready to engage with the ideas at a more advanced level, the online lecture series from the world's leading physicists are an invaluable free resource. The legendary lectures by Alan Guth at MIT, the father of inflationary theory, provide a first-hand account of this monumental idea's development. Similarly, Leonard Suskind's Stanford University courses on cosmology, part of his celebrated Theoretical Minimum series, offer deep, technical dives for the dedicated student, explaining the mathematics and physics with patience and brilliance. And of course, for readily accessible, engaging, and regularly updated content, the world of YouTube is a powerhouse. Channels like PBS Space Time offer meticulously researched episodes that tackle complex topics like CMB anomalies and the physics of inflation with both intellectual rigor and creative presentation, perfect for satisfying a quick curiosity or falling down a wonderful rabbit hole. These resources, from the foundational texts to the dynamic online lectures, form a complete toolkit for anyone who wants to move from being a passive observer to an active participant in the greatest story ever told. The cosmic microwave background radiation is more than just ancient light. It is a time capsule from the universe's dawn, offering unparalleled insights into its origin, composition, and destiny. From the serendipitous discovery by Penzias and Wilson, who first heard its faint hum through a radio telescope plagued by pigeons, to the breathtakingly precise maps created by satellites like COBE, WMAP, and Planck, this field has transformed completely. We've journeyed from mere speculation about the universe's beginnings to a rigorous, data-driven science of precision cosmology. This ancient glow has revealed a cosmos far stranger and more magnificent than we ever imagined, one dominated not by the familiar atoms and light we see, but by the mysterious, invisible forces of dark matter and dark energy, a universe shaped in its first fleeting moments by a period of hyper-expansion called inflation. Yet for all we have learned, the story is far from complete. Profound mysteries remain, each one a beacon guiding the next generation of explorers. The true nature of dark matter and dark energy continues to elude us. The unsettling Hubble tension, a discrepancy in how fast the universe is expanding, hints that our standard model might be missing a crucial piece of physics. The hunt for the elusive B-mode polarization, the smoking gun of primordial gravitational waves, continues with ever more sensitive experiments, and the strange anomalies in the CMB itself, the curious cold spot, the puzzling axis of evil, whisper that there may be even more profound surprises hidden within this ancient light, waiting for a sharper eye to decipher them. This is the beautiful, unending cycle of science. Each answer unravels new, deeper questions. The study of the cosmic microwave background is a testament to human curiosity, collaboration, and our relentless drive to understand our place in the cosmos. It connects the quantum flicker of the first instant to the vast galactic cities we see today, weaving a single, coherent narrative from the Big Bang to the present. So the next time you look up at the night sky, know that you are not just looking at points of light. You are gazing back in time, seeing a historical archive written in the faint, cold glow of creation itself, a story that began nearly 14 billion years ago and is still being told. We encourage you to share your own thoughts and wonders in the comments below. Subscribe for more journeys into the heart of space's greatest mysteries, and never stop looking up and asking